Today we shall calculate the curl of the electric field E due to static charge distribution. We will first consider our simplest possible configuration, which is a point charge placed at the origin. So here I have my point charge Q placed at the origin. Due to this point charge, there will be an electric field E in the space around the charge. Now let me take 2 points A and B in the space. The distance of point A from the charge is RA, and the distance of point B from the origin or the charge is RB. Now consider a path C. Consider a path C directed from A to B. The path is directed from A to B. Let's call it C. I would like to calculate the line integral of the electric field E, that is E dot dl, from point A to B along the directed path C. So to do that, consider the electric field at a point say P. Consider the electric field at a point say P on the path C, and the value of the electric field at this point will be equal to 1 over 4 pi epsilon naught Q divided by R square AR unit vector, and R is the distance of the point P from the charge Q or the origin, and AR is the unit vector directed from the origin to the point P. So the electric field E will be in this direction. The differential displacement dl at P will be tangent to the path C at P. The differential displacement dl, and its expression in spherical coordinates will be dl will be equal to dr ar dr ar unit vector plus r d theta a theta unit vector plus r sine theta d phi a phi unit vector. Now to calculate the line integral, we first consider E dot dl, and from these two expressions and from the expression of the electric field and the differential displacement, the E dot dl will be equal to E dot dl will be simply equal to 1 over 4 pi epsilon naught Q over R square dr. Now to calculate the line integral of the electric field, we just integrate E dot dl from A to B along the path C, and that will be equal to the integral, and E dot dl, and since E dot dl is equal to 1 over 4 pi epsilon naught Q over R square dr, so the integral of line integral E dot dl will be equal to the integral of 1 over 4 pi epsilon naught Q over R square dr from A to B along the path C. Now if you look at the integrand, you can see that the integral is independent of the path C chosen to reach from A to B. So I can remove this C, and since we are integrating with respect to the variable r, the limits of integration will be from Ra to Rb. So evaluating this integral, we will have 1 over 4 pi epsilon naught Q over Ra minus Q over Rb, and that is the line integral of the electric field E dot dl along the path C. This is a very important result. You can see from the right hand side that the electric field, the line integral, is independent of the path C taken to reach from A to B. It is simply equal to 1 over 4 pi epsilon naught Q over Ra minus Q over Rb. So with this, let us now consider that suppose we move from point A to B along a path C, along any arbitrary path, it doesn't matter now. So let's consider the same path C. So you move from A to B along the path C, and then you move from B and you come from B again to point A along another path, call it C star. The line integral of the electric field around this closed path will be equal to the integral E dot dl from A to B plus the integral B of E dot dl from B to A, and this will be equal to 1 over 4 pi epsilon naught Q over Ra minus Q over Rb plus 1 over 4 pi epsilon naught q over rb minus q over ra. Evaluating this will be equal to will give 0, and so the line integral E dot dl will be equal to 0. The line integral of the electric field due to a static charge around a closed path will be equal to 0. And this is independent of the points A and B. I just take them arbitrarily. Now, if you look at this closed path is can be considered as the boundary. This can be considered as the boundary of an open surface S with the unit vector to the path n as shown. It's directed as shown in the figure. Since in considering this open surface, from the Stokes theorem you can see that the line integral or the circulation of the electric field, that is the integral of the electric field around any closed path, around this closed path, will be equal to the surface integral of the curl of the electric field dot ds, and where ds is directed along the unit vector directed as shown in the figure. And since the left hand side is equal to 0 as shown above, the right hand side will also be equal to 0 for any right hand side will also be equal to 0 for any open surface S bounded by any closed path. And for the surface integral to be equal to 0 for any open surface S, it is necessary for the curl of the electric field to be equal to 0. The surface integral will be equal to 0 only when the curl of the electric field is equal to 0. So we have this result that the curl of an electric field due to a single static charge is equal to 0. Now I have I prove this for the result. I have proved this result for a field due to a single static charge placed at the origin. And you can see that the result is independent of the origin. It is independent of the coordinates. They hold no matter where the charge is located. And suppose if you have more than one charges, for example, so I have a charge q1, another charge q2, another charge q3 and q4, then by the principle of superposition, the electric field due to these charges will be equal to the sum of the electric field due to individual charges. The total electric field is the sum of the electric field due to individual charges. And if I now calculate the curl of the electric field, the net electric field, that will be equal to the sum of the curls of the individual electric fields. And since we have just proved above that the curl of an electric field due to a single charge is equal to 0 or is equal to a null vector, so these individual curls will be null vectors. And so finally we have a very general result that the curl of an electric field due to static charges, the curl of the total electric field due to static charges is equal to a null vector. This is a very important result, and this is actually the Maxwell equation. This is Maxwell's equation for electric fields due to static charges.